We're going to go into chapter 11, which is chapter 4 of the custom RCC text. This is the more advanced version, I guess you would call it, of hypothesis testing, at least the next step. Before in chapter 10, we were doing inferences on one sample. So now in chapter 11, we're going to be going into inferences on two samples, and we're going to have several sections about this. I'm going to be separating them into different, each video is going to be one section, and they're going to be somewhat quicker videos, I hope, than the previous videos from chapters 8 through 10. So when we go into chapter 11, we bring up this kind of new concept that we haven't really dealt with so much, which is the idea of independent and dependent samples. When we're talking about the two samples, or each of the two samples, are each of them dependent of each other, or are they independent of each other? So that's what we're going to talk about first, and I'm just going to introduce this a little bit. You may see some questions about this on the homework. I'm going to let you guys kind of figure it out because it's pretty straightforward, but the idea is we have two different possibilities in chapter 11, at least a lot of the section in chapter 11. So in chapter 11, which is inferences on two samples, first off, if you remember, the Math 244 students, you're in inferential statistics, and really business stats is also inferential statistics. And the idea, if you remember, making inferences is the idea of looking at a sample and being able to tell what the population looks like based off the sample. And that's kind of the whole idea of actually chapters 8 through 10, and actually this whole entire term is based off of inferential statistics. So actually more chapters 9 through whatever. Chapter 8 is kind of a building block of what we'll be using the rest of the term, but that wasn't really inferential statistics. Anyways, so we have the idea of these two samples. We'll call them sample X and sample Y, coming from populations X and population Y. We're saying X and Y can be dependent of each other, or X and Y could be independent of each other. The only place we've seen independence before is actually like before chapter 11 is talking about each individual samples have each value or that comes from each of the variables. They have to be independent of each other. Like all the values in X, there may be 20 of them. Each of those 20 values must be independent of each other. Now, this is kind of a different concept when we're talking about it in chapter 11. We're dealing with more than one variable. We're talking about each of the individual variables are independent of each other or dependent of each other. So, and we'll see some interesting things involving that. So we can deal with what's called, what's known as independent variables. Or we'll be dealing with dependent variables throughout chapter 11. And dependent variables is also known as, dependent variables is also known as matched pairs. Okay. So matched pairs is the same thing as dependent variables. You might see both these vocabularies. Just know that they're the same thing. So anyways, I'll let you guys read up on that, and that's all I'm going to really say. But we'll be going into, I'll go over an example of an independent and dependent variables and work out the hypothesis testing of each of these. So anyways, let's go into the first example, or the first idea, which is the independent samples case. So it's very similar to Chapter 10, the process of the hypothesis testing, and just the idea of how it all works. Let's just talk about the sampling distribution. The sampling distribution, so of an independent, of two proportions that are independent of each other. So, if we're wanting to compare two variables, two proportions, or if you remember, proportions are also known as the Bernoulli distribution. But if we're comparing two variables that are a Bernoulli distribution, if we're going to compare them, we would want to take the difference of the two variables to compare them and see how close they are to zero. If they're really close to zero, the differences, then the two variables are somewhat alike. And if they're really far away from each other, then they're not alike. So we have a new distribution, a sampling distribution, and that's p hat 1 minus p hat 2. So we're going to be talking about the sampling distribution of this. So the idea is we have one population that we're going to take, that's a Bernoulli distribution. We're going to take a sampling from that, get a p hat, and then we're going to do the same thing for population 2, get a p hat, and find the difference of the two samples. Okay, and that's the way we can compare the two populations based off samples. So the sampling distribution. So we would say that similarly, I mean, you can compare this to proportions of one variable. We would call the center of this distribution, the sampling distribution, mu of p hat 1 minus p hat 2. This is subscript right here, p hat 1 minus p hat 2. Before we just had mu a sub p hat. Since we're finding the difference of the two variables, we have this subscript here. Okay, and this can be estimated since we know when we're talking about sampling distributions like Chapter 8, we know what the population looks like. So the best estimate of, or the center of this distribution is P1 minus P2. Okay, and the standard deviation of p hat 1 minus p hat 2. Now this is kind of weird, and notice that we're taking the difference of the two variables, right? The sampling distribution, we're taking the difference, and then but notice that the standard error or the standard deviation of the sampling distribution, means the same thing, is that should look familiar to you, divided by n, and n1 meaning the sample size of the first from the sample size taken from the first population, plus, now that's kind of weird. I mean, where did this plus come from? You might be thinking that, so that's a good idea to be thinking that. We get this crazy looking thing. Now you're going to actually be proving something similar to this, involving plus at least, in your week 5 class discussion. And I gave a lot of hints, and anyways, you'll read up on that. And anyways, we have the same criteria in order for this to be a normal distribution. That being that we need, first off, n1 p1 hat 1 minus p1 hat to be greater than or equal to 10. But also, since we're taking two samples, we want n2 p2 hat 1 minus p 2 hat to be greater than or equal to 10. We need both of them to be greater than or equal to 10 in order for this sampling distribution to be normal. Okay? And we also, well, yeah. Anyways, so you may realize that the z-score would just be essentially this minus this divided by this. Okay? They mentioned that in the text, but if you wanted to calculate a z-score, it's very similar to before. We take the sample, we subtract the mean, and we divide it by the standard deviation. Okay? All right. So anyways, that's about all I'm going to be talking about from this this part. We're going to go into the hypothesis testing. So the hypothesis testing involving two proportions, the difference of two proportions. We're going to get into that. So first off, similar to Chapter 10, we have preliminary checks that you have to do. For a hypothesis test of regarding the difference between two population proportions, so the difference between two population proportions. So, and you may realize it's good to be able to do this by hand, but there is a on your TI calculators, graphing calculators, you'll notice that there is a way to do this with your calculator, and I'll just tell you right now. It's the true prop Z test. You'll find that under stat and then tests, and then you'll find two prop Z tests, and it's pretty self-explanatory of what goes where. Anyways, take a look at that if you want a shortcut of finding the test statistic and the p-value. But the general process is the same from Chapter 10. It's just kind of taken to the next level. So as you may, if you compare the checks, like from Chapter 10, there's checks that you have to take. They're very similar to it's very similar to the checks from Chapter 10. We'll notice. First off, we have this extra check that the samples are independently obtained using simple random samplings or through a randomized experiment. So that's similar to before. So we need independence and randomized experiment. Again, similar to before, you can find in the book in section 11.1 and so forth 4.1. You can find the purple section, which goes over all the steps of a hypothesis test. So it's just looking at that for details. And now we also need to check that that we have that NP1 minus P is greater than or equal to 10. You have to check that still for each of them, similar to the sampling distribution, in order to have a normally distributed sampling of the difference between two pop proportion sampling distribution, or the sampling distribution of the difference of the two variables. So anyways, and then they also have this check of the sample size has to be less than or equal to 5% of the population. That's to ensure that you have an independent sampling. So anyways, that's similar to Chapter 10 for proportion. And that has to be true for both the first and second population. Now, there's also, I'm just going to mention one thing actually. I don't want to go through all the steps. I just want to go directly into the example as fast as possible. There's this other idea of what's called a pooled estimate. The pooled estimate of P. So first off, you should realize that that if you think about it, if you look back at chapter 10 when we're doing proportions, we're using the P on the denominator, and on this like standard error part of the test statistic. And you'll notice in chapter 11 that we're unable to use an estimate of what P is. It's because we're taking the difference. We have no estimate of each of the P's. So what we use what's called a pooled estimate of P, and we denote this P hat. Notice we have P hat 1 and P hat 2 we're taking the difference of. The pooled estimate is the P hat, and this is equal to P hat 1 plus P hat 2 over N1 plus N2. We're going to be using that on the denominator of our test statistic. Okay, and I'll show you where that comes into play, and I'll mention it. So I want to go directly into an example, and a good example to maybe start out with is let's go ahead and do number 23 on the section 11.1 exercises, and it has the bolded right next to the number tattoos. So let's go into that example. So 23. So if you read the problem, you can pull out some information, and you'll notice that of the 1,205 males surveyed, 108 responded that they had at least one tattoo. So notice that this would be the first population that they gathered a sample from. So this would be actually P hat 1 equals, and specifically X1 over N1, which equals 181 over 1,205. So it's very similar to chapter 10, but we have to have a subscript 1 because we have two different populations. You can't just quite simply say P hat equals X divided by N, because there's two different populations. We have to denote those populations with subscripts. Similarly, we have P hat 2, and that comes in the next sentence, of the 1,097 females. So apparently they're comparing males to females. They separated the two populations. So 1,205 males, 1,097 females. So we have equals X2 over N2, and that would be 143 over 1,097. And without even reading the problem, you can kind of just tell that they want to figure out, I don't know if it's a left tail, right tail, or two tail test, but you can obviously tell that they want to figure out which gender has more tattoos. We can read into the wording down here. Oh, actually, we can see that this is an example of a confidence interval. I didn't read that. Let's go ahead and do that. So this is kind of like a chapter 9 problem where we're building a confidence interval. Very similar, and you can kind of tell the differences. So construct a 95% confidence interval to judge whether the proportion of males that have at least one tattoo differs significantly from the proportion of females. So differs significantly. It's not saying one over the other, but well, anyways, mine's stuck on hypothesis test. No, we're doing a confidence interval, but anyways, we're building a 95% confidence interval. So similarly to before, we would want to figure out Z alpha over 2 since we're doing a confidence interval. And 95% still 1.96. That shouldn't surprise you. Now the equation for the confidence interval, and now we're still doing the difference. So we're building a confidence interval, interval for P1 minus P2. So notice that these are population differences because we're trying to estimate what the difference is of the population. And we're going to do that with the sample, inferential statistics. Okay, so the confidence interval for P1 minus P2 is P hat 1 minus P hat 2. That's the point estimate, plus or minus, I'm going to put parentheses around it to represent point estimate, plus or minus Z alpha over 2, same as before, we use the critical value, times the square root of the standard error. And the standard error for the difference of two the difference of two proportions is you may remember. Well, actually, we haven't talked about this, but yeah, we did. Yeah, that we have. P hat 1 divided by, or times 1 minus P hat 1 divided by N 1 plus, there's that plus again, P hat 2 1 minus P hat 2, squeeze a parenthesis over there, over N2. Okay, so that's the standard error. Okay, there's the critical value. There's the point estimate, and still this whole thing with Z and the critical value times the standard error is still also known as the margin of error, same as from chapter 9. So let's go ahead and plug in the values that we know about, and we should be able to find the confidence interval. So it's just plug and chug from here. So 181 divide 1205 minus 143 over 1097 plus or minus 1.96 times, now I'm going to let you go ahead and plug in the appropriate values here. And I'm actually going to, you can check this. See if it's just plug and chug and figure it out. I think you can kind of see where you plug it all in. And I'm going to show you actually something else you can use. It's on your calculator. And it is the 2 prop Z, not test, but interval. Should make sense to you. 2 prop Z interval. We're going to go ahead and do that really quickly. And I'll pull it up. Stat tests 2 prop Z interval. Where are you? Two prop Z interval right there. And X1 in this case, as we mentioned, is 181. N1 in this case is 1203. 143. 1097. We're doing a 95% confidence level, as mentioned. And we're going to calculate. And I got the values from this. I end up getting the confidence interval 0.0083, 0.04848. All right. So now what's kind of weird is the interpretation of the confidence interval. And now this goes back to reading the problem. construct a 95% confidence interval to judge whether the proportion of males that have at least one tattoo differs significantly. Now, as we mentioned before, if the differences, if this difference is 0 right here, then there would be no difference, right? That would represent no difference. This is equal to this, therefore the difference would be 0. So that is what we're looking for in the confidence interval. Notice that this, so we've found the confidence interval. We've done the first part. Now we need to figure out if there is a difference. And based off this, we can actually state the actual conclusion of if we were to do a hypothesis test on this, a two-tail hypothesis test. And we would actually say, do not reject what would be H naught. And just to let you know, if we were doing a hypothesis test on this, the H naught would be equivalent to P1 equals P2. Or equivalently, this is also equivalent, if you imagine subtracting the P2 on the other side, P1 minus P2 is equal to 0. So we're actually saying do not reject H naught because we notice that 0 is contained in this interval. So based off of 95% confidence, we would say that the difference of the two variables, there's no that there's no difference between the two variables. That's what we would say. So that's the same thing as saying do not reject, essentially. Hopefully you can kind of see that. I would like to go over an example of a hypothesis testing of this, just to see another example. It will always help to see another example. So the idea, so if this did not contain 0, like let's say the interval was this, notice that this interval right here does not contain 0 if we take away that negative, then we would reject H naught because it does not contain 0. Okay, so kind of weird how we do this, but if you just think about what it means to for P1 to equal P2, that's saying that P1 minus P2 is equal to 0. 0 is contained in here, therefore we do not reject that the difference is 0. Okay, or equivalently, P1 is equal to P2. All right, so kind of weird interpretations, and you can do think about even rejecting or failing to reject with with a confidence interval. Let's do specifically. Let's do a hypothesis test, straight up hypothesis test. So I'm just going to make sure I choose the problem that is a hypothesis test. Okay, let's do 21. 21's good. I promise. So 21. Abstain from alcohol. Okay. So this problem is a hypothesis test. And it doesn't say build a confidence interval. And okay, so anyways, we can see on number 1, we can find, or the first thing I mean, let's just write down a few pieces of information. We know that x1 equals, actually let's just say p hat 1 is equal to the first set of x and n's. So we would see 407 over 1100. Okay. And then we would see 333 divided by 1100. All right. So, and then we also see alpha equals 0.05. All right. There's the three pieces of information, and the only other piece of information that we really need to pull out of this is to know if it's the left, right, or two-tailed test. And it says, has the proportion of adult Americans who totally abstain from alcohol changed? And so we're comparing two different years here. Yeah. Okay, so this population 1 represents 1947, and this population 2 represents 2010. So they want to know if it's changed from here to here. So that's a two-tailed test change, not is one more or one less. So we have H naught. Oh, sorry, we're not there yet. We need to do the checks. The checks. First off, there's three different checks, but I'm just going to go over the one that I really care about, and that's to make sure that we have a large enough sample size, and that's N1 times P hat 1, 1 minus P hat 1 is greater than or equal to 10. And looking at this, it's pretty obvious. 1100 times, something that's, around 0.3 times 0.7, I don't know. That's obviously greater than or equal to 10. And similarly, we can tell that N2 P hat 2 times 1 minus P hat 2 is greater than or equal to 10. So we have a normal distribution for the difference of the two proportions. Okay, let's go ahead and go into step 1, which is H naught. H naught would be the difference of the two proportions. P1, or another way of saying that. Now, again, there's two different ways of saying this. We can say that P1 equals P2, or we can say P1 minus P2 is equal to 0. Okay? The alternative hypothesis, since it is a two-tailed test, similarly to before, we say not equal. We're comparing two different populations. Okay? And that is equivalent to saying P1 minus P2 is not equal to 0, right? By subtracting P2 on this side. Okay, and then we also have step 2, which is alpha. We know alpha equals 0.05. And step 3, hopefully you can kind of see a parallel of chapter 10. Very similar. Step 3 is when we find, actually steps 1 through 5 are identical, like in what you're trying to do. Null and alternative, level of significance. Now step 3. And Z naught is equal to P1 minus P2, or P hat 1 minus P hat 2. So that would be 407 over 1100 minus 333 over 1100. Now notice that we would write this. So minus the population thing, right? You'd take this and subtract the next part. But notice that P1 minus P2, we usually put the claimed value over here. But the claimed value of P1 minus P2 is 0. So we'd just be subtracting 0. So it's just P hat 1 minus P hat 2. Okay? We're just subtracting 0. There's no need to ever use that. And we'll notice that's the same thing for the mean when we get to that. For chapter 11. And so now what we have is the square root of the standard error. And that would be 407 over 1100 minus 333. Oy, what is wrong with me? Times 1 minus 407 divided by 1100. divided by, so P hat 1 times, forgetting one thing, the pooled, what did we call it? Sorry. Making errors. That's why I do not live videos, but just give you the errors as I would do in class, possibly. The pooled estimate of P, that's what it's called. We want that in here. I forgot about that. So notice in chapter 10, when we're doing proportions, we do the difference. We use the population value down here, and we don't actually have the population value of what each of the P values are, like P1 and P2. So what we have to use is the pooled standard deviation, which is the best estimate of what each of the P1s and P2s are. So let's go ahead and do that. Now that's the other piece of information we would want to do, which is the pooled pooled proportion, which is equal to 407 plus 333 divide 1100 plus 1100. Okay? See that? So we have x1 plus x2 divided by n1 plus n2. Okay? That will give us the values that we need. So this isn't actually down there. What we actually have is this p hat 1, which is or p hat, which is this value right here, times 1 minus p hat, that fraction again, times, so that's the square root of that, times the square root of 1 over 1100 plus 1 over 1100. Okay? So that's one big difference between the standard deviation, or the hypothesis test, and the confidence interval. Notice I did not use the pooled estimate of P in the confidence interval, but we had to use that here. You just substitute this value right here and right here. And I'm going to calculate this with the calculator really quickly. And I'm actually going to use, now I told you about this, I'm going to use the 2-prop Z test to actually solve this. You can use this. It's under Stat Tests, 2-prop Z test. And 407, X1, 1100, N1, 333, X2, and N2 is 1100. And as we mentioned, it's a two-tailed test. And calculate. And this equation right here, we can do it by hand. You can check. We would actually get this to be equivalent to what we see here for Z, 3.34. Okay? And you can actually get the p-value from this, and the p-value is 8.4 times 10 to the negative 4 power, which is a really, really small decimal. So that's way out there, which makes sense with the z-score. So let's continue here just to picture what's going on here. So, drawing a normal distribution, you know I like doing this to compare the critical value. And remember that alpha is equal to 0.05. Or is it? I don't remember. Alpha is equal, 0.05. So that would give us, for a two-tailed test, that would give us the critical values 1.96, 1.96, and that is equal to Z alpha over 2. Okay? And those are the critical values. So this is the boundary of reject and fail to reject. So this would be the reject H naught over here, and reject H naught over here, and this is the fail to reject H naught in the middle. So where did that test statistic lie? And we found out that we have what, 3.34, did I say? Yeah, 3.34, which is way out here. 3.34. Way the heck out there. So obviously we failed to reject H naught. Since we noticed that 3.34 is not in between these two values. So we're rejecting H naught. And so this is, again, is Z naught, or test statistic. So we reject H naught, and step 5 is to state the conclusion. And again, the flow chart, does the conclusion have the condition of the first step is, does the statement have the condition of equality? And as we can see, if we read the problem, and this can be a little bit tricky when you read this, we'll just read it. Has the proportion of adult Americans who totally abstain from alcohol changed? So they're saying, has it changed? So they're saying it's not the same. Condition of equality in this case, when you're figuring out the difference, so P1 minus P2, sorry, it's actually P1 equals P2. That would be the condition of equality. Are they saying that they're the same? No, they're wondering, has it changed? So it is not the condition of equality. So I would say no for step 1 of the flowchart. Step 2, did we fail to reject? We reject. Or, wait, what does the flowchart say? I'm trying to remember the flowchart off the top of my head. Did we reject H naught? Yes. So based off this, we can write down all the information, which would be on this would give us option 3, the third one down the list. So you would just state word for word what it says there, and then when it said ... claim, similar to chapter 10, we would just write down the claim. The proportion of adult Americans who totally abstain from alcohol has changed. And then you would put with 0.05 level of significance, or alpha equals 0.05 level of significance. So let me have, if you're having questions about how to use this, whoever took Math 243 with me, it's kind of obvious because we used that last term, that flow chart. Please let me know if you have any questions about this. You're going to be using it on your final project, because you're going to have to state in words what the conclusion is, and it'll help for your homework too, possibly. So please let me know if you're having any issues with this. And yeah. And just the p-value approach again, the p-value approach is comparing alpha to the p-value. So alpha is 0.05 and the p-value is really, really small. And since alpha is larger than the p-value, we would reject H naught also. So that we should get the same conclusion with the p-value approach. All right, so anyways, that is the example of we've gone over 2 different examples, one involving the confidence interval and one involving a hypothesis test. The same ideas, but one big difference especially is that that idea of the pooled, gosh, I don't know why I'm forgetting what it's called, the pooled estimate of P. Use pooled estimate of P in the hypothesis test and not in the confidence interval. So anyways, you can read up a little bit about that if it didn't really make sense, but we saw it worked out through this video. Now, that was the example of independent. That's what you do with an independent. Now, what happens if the 2 variables from the 2 populations are dependent of each other? So an example of this is Let's just find an example really quickly. Problem 33, hazardous activities. So what they're doing is that they did a survey of 3,029 adults, Americans, that and people, whether they smoke cigarettes and whether they also wear a seatbelt in a car. So they have two different variables. Variable one, or pop. So variable one is seatbelts. And variable two is cigarettes, I guess. There we go. Smoke, I'll just say. And you get this chart here. And the idea is they'll write down the information of if they smoke and if they have no seatbelt. So there's 67 people that smoke and do not wear a seatbelt. And then they have, do they smoke and not wear a seatbelt, 327. And similarly, we get they wear a seatbelt and they smoke, 448. And they wear a seatbelt and they do not smoke, which is 2,187. And the question that they're determining, let's read the question of why is this a dependent sample? And as we can see, these variables are obviously dependent of each other because you're asking the same people, the 3,029 people, both questions. So the idea is we're dealing with one population and two variables, and you obtain this dependence because it's coming from the same population. So that's where you're getting the dependence part of this. So that's why it's a dependent sample. That's part A. Is there a significant difference in the proportion of individuals who smoke and the proportion of individuals who do not wear a seatbelt? Now this is kind of goofy, and the equation is mentioned here in the section. And we have this test statistic. I'll let you read through this example, but it's pretty straightforward, the calculation compared to the independent case. But you have this test statistic. It's Z naught equals, so apparently this follows a normal distribution, or a standard normal distribution, minus F21 minus 1 over the square root of F12 plus F21. So you may be wondering what this represents. And so what we want to do is we want to figure out the differences. So the question that they're asking is I lost the page. Is there a significant difference of the proportion of individuals who smoke and the proportion of individuals that do not wear seatbelts? Is there a difference between them? Or is there a difference between the proportion of individuals who engage in hazardous activities? That's another good way of thinking of it. And what you want to do is you want to compare where they different, where they differ. Like if one is being hazardous in one variable, and then you want to look at where they're not being hazardous in the other variable, and vice versa. So, or the idea in general is success in one, failure in the other, and then failure and success, and use those two values. Okay. So, and we want to know if there's a major difference between those two, what they call differences, those two different hazardous activities. So what we would use in this case is the 327 and the 448. Okay, so this is equivalent to, oh, and just to let you know, that you only do a two-tail test. You only do a two-tail test with actually. Just looking here. Oh yeah, that makes sense. You only do a right-tailed test. Well, it is a two-tailed test, but you'll only get test statistics that are on the right tail. Because if you think about it, if you take the difference here, chances are it's going to be, somewhat of a large number since we're doing counts. So this will be positive. Subtract 1, and then you divide by another positive number. So Z naught is always pretty much going to be positive. Okay, so the idea is, okay, so what we would do here is 327 minus 448. And it doesn't matter which one you choose to be 1, 2, or 2, 1. So it didn't matter if you do 448 minus 327, as you can see, because we're taking the absolute value. Subtract 1 over the square root of 327 plus 448. And the sad thing I know about this is that there's no there's nothing on your calculator to, like 2-prop whatever test. You have to do this by hand. But good thing is it's not that complicated. So we have 120 divided by second square root of 327 plus 448. So I got 4.3. There's our test statistic. And as you know, well, actually, what is our level of significance? Our level of significance for this problem is alpha equals 0.05. And since we're doing not equal, we would have 1.96 and negative 1.96. And as I mentioned, you probably won't have to worry about this because it's always going to be positive. As you can see, this one's positive. And we're out here at 4.3. And that is in the rejection region, same as the idea as the last test. And fail to reject region is towards the middle. Okay. And to let you know, the H naught for this is the proportion between the. So remember, similar to before, you always have equal for null. So just to go over this really quickly. I'm kind of going out of order, kind of unorthodox way of doing this would be one of the first steps. We would say that the proportion between two populations are equal. So the proportion between the two populations is equal, and the alternative is the proportion between the two populations are different. I said it in words. You can write it down. That's word for word. It's kind of always the same for dependent proportions. And the checks you have to do would be the first thing you would do for the hypothesis test. The checks you would do is you want to, in order to do this test this way, you have to have dependent samples. There you go. And they have to be randomly selected. Okay. And now, kind of a weird thing is F12, to make sure you have a large enough sample, is that you have to make sure that these two cells, which would be 327 plus 448, it has to be greater than or equal to 10, which is obviously met for this example. There's your other check. There's only two checks for this. Okay, and the conclusion that you would state here, you use the flow chart still. Do we have equality? What they want to know is, if you look at the wording, is there a significant difference in the proportion of individuals? So difference, that is not saying that they're the same or equal. So that would be no for the first part of the flow chart. Second part of the flow chart, did we reject? Yes, we did, since our test statistic is over here. And so we rejected. So that would be a no, yes. We're at option 3. You would go through the process and say, blah, 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 whatever the flow chart said. And then you would say that the proportion of individual that blah, 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 blah. There's a significant difference with the proportion of individuals who smoke and the proportion of individuals that do not wear a seatbelt, with alpha equals 0.05 level of significance. So I'm hoping you guys are maybe getting familiar with this, but please let me know if you want me to walk through an example of how I use the flowchart. I'm not really showing you the flowchart here, but I'm hoping you guys are kind of picturing this, and the idea of how the first, especially the first step is the difficult thing, is does the claim have the condition of equality? Okay. And the only other thing that that they talk about in this section is the idea of, do we have a large enough sample size? And this is very similar to, but taken to kind of the next level. Sample size for estimating P1 minus P2. Do we have a large enough sample size to have a small enough margin of error? Same idea from before. When we're doing confidence intervals. But in this case, we have two different sample size ends. So you're to make things simplified, you're going to say if you that the sample size is for N1 and N2 are the same. So we're saying N equals N1 equals N2. Okay? That's the sample size needed is N. And that's saying that we need to take the same sample size from each population. And the equation, if you were to solve, I'll just go back, similar to how I would have showed you before. If you were to solve this equation right here, assuming that this N1 is equal to this N2, like we are for figuring out the sample size, you'd be able to simplify this a bit because we have the same denominator. Because we're assuming that N1 equals N2, so those two are equal, so they have the same denominator, and we would be able to simplify this with algebra and solve for N, okay? If we were to solve for N, we would get the equation that's mentioned in the book. P hat 1 times 1 minus P hat 1, P hat 2, 1 minus P hat 2, plus in between there, and then z alpha over 2 e, still our margin of error, which will be given to you in the problem, within whatever, that's e, remember, that would be your equation. So it's very similar to what we had before from chapter 9 for determining the sample size. You would probably see some, that looks familiar. But now we have this extra plus the other variable. We want this entire thing to multiply to this, so we need parentheses here. Yeah, there we go. So this entire thing times this, okay? And remember, that is if we have a pre-assumed value of what, if we had prior estimates of our P1 and P2. But if we do not have prior estimates of P1 and P2, we would be using 0. N equals N1 equals N2. This is just like proportion confidence intervals, and we wanted to figure out the needed sample size to have a small enough margin of error in our confidence interval. And we did not have a pre-assumed value, and it's just unavailable. We'd be using 0.5. Remember, before we had 0.25, but imagine this being 0.25 plus 0.25, like we did in chapter 9. Add those together, you get 0.5 times z alpha over 2 divide e, margin of error, squared. So that should make sense. And kind of analogous to what we did in chapter 9. All right. Anyways, that is it. And kind of all the concepts that we would be using. Let me know if you want to go over specific examples, and we can do that one-on-one. And we can work on problems just like this, but it would be live, working one-on-one with each other. Okay? And great. Oh, and just to let you know, give you a heads up, week 5 class discussion, number 3, there's that Excel spreadsheet. I'll give you a heads up, and this is good if you watch these videos, you'll know this. It's involving proportions, because you see a bunch of zeros and ones on the first couple tabs. That's your Bernoulli distribution. Okay? So, anyways, just heads up. And you'll have to still kind of figure out and look into that Excel spreadsheet to figure out what's the rest and answer the questions. Okay, logging out here.